Hey everyone, this is the second lecture for chapter 16 on waves. So in the first lecture, I talked about just ideas like frequency and wavelength, and I discussed a wave on a string and how the wave speed is connected to the tension and the mass density of the string. We also talked in that one about the wave function, which is the y of x and t. So hopefully you recall that. For this lecture, I just wanted to first of all take a look at the chapter 16 topics. So again, the first lecture we covered transverse waves and wave speed on a stretched string, which is the first two sections of this chapter. In a separate lecture, I will talk about energy and power of a wave. Um, but we're going to skip the wave equation, section 16.4, and phasors. Just to save us a little time, if it turns out there's more time, we could come back to that. So in this lecture, I'm going to talk about interference of waves and the standing waves and resonance. Now, if you recall from chapter 15, resonance is a case when an object gets a really large amplitude because you are pushing it at the right time. It's kind of a similar thing that happens with waves here. Uh, but so those are the topics you're going to see in the homework, 16.1, 16.2. There may be a question from 16.3, and then 16.5 and 16.7. So first of all, let's talk about interference. And I'm going to restrict myself to this chapter to wave on a string. In the next chapter, chapter 17, we'll actually talk about sound waves. But let's see here. I think what I'll do first of all, just to show you or kind of review some of the stuff we talked there. Uh, let's talk about a wave. So, for example, you could have a wave on a string or wave on water. And one of the things that I can do here is I can turn this on. And one thing you'll see, let me look at the side view. I just wanted to emphasize. So if I turn my frequency down, so now the number of oscillations per second in hertz is much slower. You can see the wavelength is much longer, right? The distance between the two wave crests is much bigger. So a lowered frequency means a higher or longer wavelength. And of course, the opposite is true. If I make the frequency really high, uh, I'm going to have a much shorter wavelength. You can see the wave crest, the waves are much closer together. And this is due to our V equals F lambda equation. Now, in the chapter 15 lecture, we talked about that the wave speed is determined by the string, by the tension and the mass per length. Similar things happen for a wave on the ocean or a wave in the water, and for sound waves, as we'll see in chapter 17. The wave speed is determined by how dense the material is, but also how stiff it is, how much force there is sort of holding the material together. So the wave speed is determined by the medium. Um, One thing I want to show here again is, let me go back and I want to show the idea of interference, and then we'll do some mathematics of it. Um, when you have two waves, they can add together, and that's the idea of interference. So now I've got two water droplets, water spigots, and I'm going to turn them both on. So I get my first wave, and for my second one, I've got two waves here, and as they propagate out, they overlap, right? And this leads to what we call an interference pattern. So the bright areas are places where the waves are adding together, and I'm getting a what I call a constructive interference. Places where they cancel each other out, they're kind of going opposite directions at these dark points. I call that destructive interference. So this happens anytime you add two waves together. And this problem mathematically would be very complicated because it's in two dimensions. But what we want to deal with is a wave in one dimension. And so I just wanted to show this. And of course, it works for sound waves or light. Light is also a wave. And so you will get these interference patterns where the waves overlap, kind of constructive and destructive places for light, sound, or water, or even a wave on a string, as we will see, hopefully. So I just wanted to show that first of all. One of the things that we're going to discuss are waves on a string. But before I get to that, I want to do some mathematics with that. So let me go ahead and now we're going to go ahead and look at the mathematical equations for this. Oh, and bring this over here. And what I'd like to show here, move this back, is the mathematics of adding two waves together. So let's take a look here. I've got two waves, and I represent them by my y wave functions, right? So I have y1 and y2 of x and t. Now the first wave, I'm going to say it has the same frequency, and remember that this k is actually 2 pi over lambda, and omega is 2 pi f. It's the angular frequency. So these two waves have the same wavelength or frequency, but they are different only in their phase. There's an extra phase angle. So I'm saying that this wave is out of phase. Now, to add them together, I'm just going to use, right? So by adding, I mean I take the sum, y1 of x and t plus y2, and I add the two waves at every value of x and t. To do that, I can just use this simple trig identity. Now, don't get A here mixed up with this A. These are different. This is the amplitude of the wave, whereas this is just the argument of this, and B is the argument of this second wave. So using this trig identity, I get 2 times the sine of A plus B over 2 times the cosine of A minus B over 2 when I add those together. So just using those arguments, I can see that A plus B, it gives me this, 2 times kx minus omega t plus phi, and A minus B just gives me phi. So now the point here is that when I put that together, I get this final expression here. So I have a maximum amplitude of 2A. It's twice the amplitude of either individual wave. It is what I would call a traveling wave, right? It still looks like it's got this sign of kx minus omega t. So it means it's moving to the right at its normal wave speed. So it's a traveling wave, but now the amplitude part is sort of modulated. In fact, I can see, right, for example, if cosine of 0 is equal to 1. So if my phase is equal to 0, well, it makes sense, right? My amplitude is just twice the amplitude of either one because they are in phase. They kind of just overlap. Now, what if cosine, or let's say actually phi, is, let's see, pi? Well, cosine of pi over 2 is 0, right? And I will get 0. The waves will actually cancel out. And if you think about it, by changing the phase by pi, you're actually going the other way, right? Pi is 180 degrees, so one is going down and the other is going up. They cancel each other out. And this is our destructive interference case. Now, one thing to recall, if I'm talking in terms of wavelengths, if I go through pi phase or 180 degrees, this is what I would call a 1/2 wavelength shift. So the second wave is sort of out of phase by half of a wavelength with the first wave. And maybe I can draw that here, but I'll draw it here in a second because I wanted to talk about our third case. What if phi was equal to 2 pi? Now 2 pi is 360 degrees. So now you've gone around and now you've come back up. The waves are back in phase. Cosine of 2 pi is 1 again. And this is our constructive interference case. So what I'm trying to show here is that anytime the phase is out of phase, right? It's opposite, I get destructive interference, but anytime it's in phase, and this 2 pi phase change corresponds to a full wavelength shift. So the idea is anytime I shift the wavelength by a full wavelength, I get constructive interference. If I shift the wave by half a wavelength, it's destructive. So maybe let me try to draw a picture of that. So let's say I've got our first wave. So it looks something like this. Now, if I were to shift it by half a wavelength, I would move this over there. And now my second wave would look like this. You can see it's totally what I would call out of phase. One's going up while the other is going down, and this is 0. They cancel each other out. This is our destructive interference. On the other hand, if I took this original wave and I shifted it by a whole wavelength, so I just move this all the way over, I basically just have the same wave again. And this is our constructive interference case. So now the wave will add up together and I will get something that is twice the amplitude. So hopefully that shows you what happens, kind of connects the mathematics to the picture of what's happening to the wave. And of course, I could shift the wave more than just one wavelength. I could shift it 2 or 3 or 4, and I would still get this constructive interference case. Okay, so hopefully that makes sense. I want to talk now about another situation where interference happens. And this situation is, what if I had not two waves that were sort of out of phase necessarily, right? They don't have this phase angle, but they're moving in opposite directions. You can see that they're going to add together at certain points, right? Some parts of the wave are going to be going up while the second wave is going down and vice versa. We should get an interference situation there. Now, I can write a wave that's moving to the right, if you remember in the first lecture, by putting a minus omega t. This corresponds to a wave that's going to the right, whereas my second wave here has a plus omega t, and that corresponds to a wave going to the left. So they are going opposite directions. I'm just going to add them together using the same trig identity. And when I do that, I get a plus b just equals 2kx, a minus b is 2 omega t, and my sum of the two waves is 2a sine of kx times cosine of omega t. Now notice, this is not a traveling wave. It is not a wave that's moving right or left anymore. It's actually a wave that is not moving at all. It's standing still. And hopefully I'll show a simulation of that here pretty soon. And I'm also going to post a couple other videos showing that. But what you can see is that the amplitude depends on the position x. So if I'm looking at the string, at different points along x, I may have a different amplitude. And so I'll get that a certain point of a string may be oscillating like this, maybe a second point not oscillating at all if its amplitude is 0, and so on down the string. Now, it only happens that I can get a big amplitude in certain particular cases, and those cases can be found by looking at the math. But I want to look at it in a different way. I want to look at it from more of a pictorial viewpoint. And these standing waves, when you consider them on a string, they also correspond to sound waves in a pipe, as we will see later in the next chapter. But what will happen is when you get these standing waves, they happen on a string because if I shake one end of the string up and down, a wave will travel. And then when it gets to the end, it will reflect and come back. So a wave on a string, I get these incoming waves and reflected waves, and they're overlapping and interfering. And what I'm trying to show here is the string, and at each point I'm looking at the amplitude, right? So when you watch the string, it doesn't actually look like this. This is just indicating the amplitude. If I were to take a single point on the string it would oscillate up and down between my amplitude points here, right? So the amplitude over here is much smaller than in the middle, for example. Now, as you will see in the videos I'll post later from YouTube, you only get these certain patterns at certain frequencies called harmonics, harmonic frequencies. So the picture is, let's say you have a wave on a string and you can turn up the frequency starting at 0. At 0 hertz, you won't get anything. There will be, the string will be flat. But as you turn the frequency up, eventually you get to this harmonic, this first harmonic frequency. You could call it a resonant frequency because you have to have it exactly that frequency, and then this pattern will appear, the first harmonic. Now, as you increase the frequency, that first harmonic will go away and the string will become flat again. But as you go higher and higher, you'll eventually get to a frequency that will produce this second harmonic. And you can go to a third harmonic, fourth, fifth, right? And so the fourth harmonic would have 4 loops, or 4 what sometimes people call these antinodes. So an antinode is where there's a large amplitude, and the point where there is basically 0 amplitude is a node. Right, so in the second harmonic, I have 2 antinodes. In the third, I have 3, and so on. So let's figure out what frequencies these harmonics occur at. Well, just looking at the string, if the string has a length L, maybe you can see that the wavelength here, this is only half of a wavelength. So to get a full wavelength, I've got to go twice that. So this first harmonic, my wavelength is actually 2L, twice the length of the string. And then I will remember our wave formula, that V is equal to F lambda, or frequency is speed over wavelength. So I get V over 2L. So the frequency is going to depend upon the speed and the length of the string. And I will do a numerical example here in a minute, but that is our first harmonic. When I go to the second harmonic, what changes is the wavelength. The wavelength becomes shorter. It's now equal to the length of the string itself. And so my lambda is L. My frequency then is V over L. So I'm going to have a higher frequency and a shorter wavelength for this second harmonic. And that's the general pattern. As I go to the third harmonic, I'm also going to get an even shorter wavelength and a higher frequency. So we'll just end here at the third harmonic, but you could go to the fourth, fifth, and so on. But for this third harmonic, maybe you can see that the wavelength is 2/3 the length of the string, right? I've got 2 loops or 2 antinodes. That is 1 wavelength. So lambda is 2/3 L, and my frequency is V over lambda. So V over 2/3 L, just flipping that over, I get my frequency is 3V over 2L. So I could keep doing this for whatever n harmonic I want. So in general, n will represent the number of antinodes. It's an integer, 1, 2, 3, and so on. We've done up to the third, but I could do the fourth and so on. In general, what you'll find is that the frequency of the nth harmonic is the n times the speed over 2 times the length of the string. You could also write the wavelength, right? It's 2L over n. So we've got a formula to describe these harmonics. Now, why do they happen? Again, I just want to emphasize, for example, take this second harmonic. What's happening is you've got a wave from the left side here, from the shaking of the string. It's moving this way, and then there's a reflected wave coming back. Now, you have to get the timing perfectly right so that the wave coming this way is totally out of phase with the reflected wave right at the node. And this is why it takes a very precise frequency, because the timing has to be perfect. It's exactly a resonant situation, right? And this is why it doesn't happen at just any frequency. It only happens at these harmonic frequencies. But it is due to destructive interference at the node and constructive interference at the antinode. And let's plug in some numbers. So let's take an example where maybe we have a string with a wave speed of 100 meters per second and a length of 2 meters, right? And so just plugging in the formula, my first frequency, 100 meters per second over the wavelength of 4 meters, is 25 hertz. That is my first harmonic, or sometimes people call it the fundamental harmonic. Now, if I go to the second harmonic, I've halved the wavelength and I've doubled the frequency. So now my frequency is twice as much, but, and this is typical, basically every time I go to the next highest harmonic frequency, I'm going to add that 25 hertz or whatever the fundamental frequency is. All right, and so the third harmonic, you could plug in the formula with n equals 3, and you'll get 75 hertz. You will find the fourth harmonic is 100, and so on. So these are what I call the harmonic frequencies, and here I'm showing them on a string, but they happen for any wave. They can happen for a sound wave, as we will see in chapter 17. In fact, sometimes if you blow across the top of a bottle, you get a loud sound. That's because you're creating a standing wave harmonic in the bottle or the pipe with a node, or sorry, an antinode at the opening, and so you hear a large amplitude. So I'm going to post some other videos of this. Let me actually see if I have another simulation here just to kind of show you what what I'm talking about when I talk about a standing wave on a string. So this is just a little simulation that you could play with if you want on what's on a site called OPhysics. If I play this right now, my frequency is about 50 hertz. And so if I play this, I'm getting nothing. But as I change my frequency, eventually I will get to one of the harmonics. I don't know if I can get the fundamental, but you can see I've got to get it exactly right frequency. All right, so this looks, so you can see the node here, it's not moving, right? And so this looks like the 1, 2, 3, 4, 5, 6th harmonic. Now that should be higher than the third or the fourth. So we're going to try to go down in frequency. See if we get maybe the third harmonic. We're getting close. There we go. So again, I have a node here. So I've got 1, 2, 3, 4 antinodes. So this is actually the fourth harmonic. And if you want to play with it, you could get the third here, but you got to get very precise with the frequency. And I'm not sure if I'm quite getting there. Now that's close, right? There's 1, 2, 3 antinodes there. So hopefully that just shows you a picture. This you can change the wave speed by changing the tension and the linear density. But I just wanted to show a picture of what happens. I'm going to post the YouTube video, not done by me, but by someone else that actually has an actual string and shows this. If you actually come to the lab this week, this next week, you will see we'll play around with a wave on a string like this. So let's see. The last thing I just wanted to show real quick maybe is, let's see, actually I can go. I'm going to look these PhET simulations. I just wanted to show you a little simulation of what happens when the wave reflects. Let's take a quick look at this simulation. And what happens will depend on how you're holding down the string at the end. So this particular simulation, I've got a string which is kind of a collection of beads. I'm going to turn off the damping and let's see what happens. I'm just going to go ahead and oscillate it. But maybe what you can see is that I'm kind of getting the standing wave pattern, but when I make just a single pulse, the reflection happens that it flips the wave over, right? So when you have an end of a string that's held down, it will actually pull down on the string and make the reflected wave come back out of phase with the original wave. Now, what if I had a loose end, right? Well, it actually stays in phase because now I'm not pulling down. There's nothing to force it down and flip the wave over. But you can see how the wave is reflecting. Now, of course, if I don't have an end, what happens? I'm not going to get these standing waves because I don't have the reflected wave to interfere with the incoming wave. So in fact, if I just oscillate, it's our good old wave just going off to infinity that's described by our y equals kx, sine of kx minus omega t, right? So that's the difference in the mathematics. A traveling wave has a kx minus omega t in the argument of the sine, whereas a standing wave has that separate sine and cosine. So I think I'm going to stop there for this video. I'll try to post some more videos about standing waves here. The other topic that you'll see in the homework has to do with energy in a wave. So energy is transferred as a wave travels down. For example, a string will transfer energy, right, as it moves down the string. If we talk about sound, right, sound can hit something and transfer energy, actually creating heat. So we'll talk a little about energy in another video.